So hello everyone. We'll be reviewing PR number 31933 today. It is about code coverage generation in using the Clang LLVM based source based coverage generation. So this PR was created because of the issue here in 31927. As you can see, I have reported here that the coverage report generation is broken for macOS and NixOS based system because of the issue that lcov does not work on yes, because of the linker issues and the outdated stuff, because the current LLVM that LLVM GCOV version that comes in the macOS based systems is 4.2.0, which is a lot behind compared to the one we are using to generate the reports. So this PR is this PR an alternative way to generate coverage report generation straight from the code that we have. So we will see. So first of all, giving you all a background in the fuzzing based systems. So for this PR, we'll be using libFuzzer. libFuzzer is a coverage based fuzzing uh, coverage based fuzzer. So what coverage based fuzzing means is there are a lot of coverage. There are a lot of fuzzing systems. Like we have random fuzzers, we have grammar based fuzzers, we we have this coverage based fuzzing, and we also have mutation based fuzzing. So these all have a little bit of difference in between them. So random fuzzing is just fuzzing within the set of rules that we define. Coverage based fuzzing is, so what happens in fuzzing is the test runs for an infinite amount of time until we see a bug or there is a failure reported during the test. So but so we need constant supply of inputs to be able to run it infinitely. Random fuzzer, what random fuzzer does is it will just randomly generate inputs and then keep the test going running, while the coverage based fuzzer, what it does is it will evaluate from what inputs the coverage is increasing, and it will try to like introduce inputs that will guide the coverage to be increased while the test is running, so that we can find more bugs and crashes. Because if we are touching a lot of part of the code, we are able to we are then testing more of the code to for bugs and crashes. So this is the ideology behind this coverage based fuzzing is. There is another fuzzing system which is very important, which is mutation based fuzzing. So what mutation based fuzzing does is uh, it will, from the given set of inputs that we have, it will create a new random input, and then it will throw it into the fuzzer. So this process goes on infinitely as we have a lot of inputs being generated. But the caveat here is that all the new inputs that is being created is somewhat related to the previous inputs that we had initially. So this is something to keep in mind. Now going into the PR, we will go into the steps. So first we'll do is we will uh, remove the build that we had previously for whatever reasons. This line has been added because there have been issues in the PR that with an unclean build, they the the object generation process, when we are executing this line here, cmake build will fail and to to counter that, we have added this line. So this problem is not at all uh, seen by the people. So yeah, the user here has reported that he could not see the profile, and when he did remove the build folder, he could run the steps and get a coverage output. So this line has been added here just because of that. Now we what we're doing is we are instrumenting the build to to be focused for this coverage generation. We are setting a compiler and the CXS compiler. We are appending the flag to uh, we are appending the flag to tell the compiler that we want the compiler to be instrumented for coverage generation. So this is how we do it. We append this profile instrumentation generate for coverage mapping, and we do it similarly for the CXX flags. Now we also, since we have changed the append flags, we'd also like to add a linker flag here, which will also be instrumented for coverage generation. And uh, yeah, so this is the configure step for build directory. And for macOS based system, if you have installed it from brew, you can use this. Also, these lines can be changed to uh, use another LLVM version if you want to, because LLVM version 19 can sometimes be broken and not behave as it should be behaving. So you can just change this LLVM to LLVM at the rate 18 or whatever version you want to have, and then it will work with that version of LLVM, given that you have already downloaded that particular version of LLVM using reinstall LLVM at the rate whatever version you want to use. So uh, yeah, so now we have configured our uh, build to be coverage specific. We will then run the build command to have us a build folder, uh, which will have objects and all. Now what we do is we'll be running the tests to generate profile data. So profile data is what our fuzzer maps the code from. So it is somewhat like there are a lot of mappings and all when we have the code, and uh, to make it understandable to fuzzer, profile data is used. So it gives it it gives the fuzzer some function signatures and all, and whatever the target have, like we whatever the target specifies it to have, and whatever we want the target to run, it will create a profile of that. And then from that raw profile, we will create a profile data, and that profile data will be passed on to the fuzzer with to not the fuzzer but the coverage generator. And we will then uh, have the coverage generation process here. We find all the raw profile data, we merge all of it, and then we will generate a report. So this is the idea behind it. There is also another PR that was added that is very closely related to this PR. Let me see if it is here. Yeah. So we also have this first for this report for first base test, which we which we can talk about if we have the time. So like going into the current PR now. So libFuzzer. So sorry, the current LLVM will like coverage generation will work for C++ code. Now the problem is that this part of the line will run the Python tests. So now Python is different from this C++. And how are we like how is this creating a profile data for this part of the code? Now what happens is uh, we have some targets written. So whenever we like test we have a test, they will be they are written in some kind of targets which which the compilers can understand for when we are like generating coverage. But this process is all will also come under the raw profile generation. So whenever we are generating profile, it will also like accommodate the step of converting this from Python functions to somewhat what the coverage generator can understand. And uh, the intermediate step between Python to something of this object where this test test Bitcoin object, or yeah, Bitcoin D object can, and like what will happen is from this Python test, this Bitcoin D object will run these Python tests. This object is in will this object Bitcoin D object will help us uncover what these profile data of this Python test will these Python tests to understand that we how to like understand this and how to like profile what type of uh, function has been sourced to that, and then it will transpile it into C++ and create a coverage report from that. So uh, going to this coverage generation, we will do this by ourselves now. So okay, so these are the steps. We don't already have built, so we'll just go and copy paste this. So now we have a bit, yeah, this is fine now. Okay, now we will want to run the build to create a build directly. So now we are having a build that is instrumented for coverage mapping or coverage generation. This will create two important object files, Bitcoin D and test Bitcoin, which will also then be used by LLVM to understand the prof raw and prof data. Also, you can see a demangler flag here. So what it does is it will create a human readable output. So what demangler does is it will create unique function signatures for every function, since some files can have same type of functions but with different data, and to make a distinction between them, what C++ does is it will give it a unique signature and have it stored as that signature only. So we want, as a human, we won't be able to understand that. So to remove that step, we use this demangler option. We are telling it to, we are giving it the profile that we generated here in build coverage.prof data. We are telling the LLVM cov to remove these lines from its coverage report. We are also telling it to generate it in HTML and just show summary and then project title. Okay, so we have created a build directory. Now we will just create a raw profile data for directory in it. Now we'll be running the C tests. This should be fast enough. The Python tests. It should take about 3 or 4 minutes of our time. So meanwhile, we can just talk about the second PR, which is somewhat related to this. So we have the same flags for coverage mapping, but we also have an additional flag here to be built for fuzzing, because we want the object file for fuzzing. This will not run the fuzzer, but will only create a fuzz profile so that we can uh, run the fuzz input once with the given corpus. So when we are running it only for a particular amount of time, or for only a particular amount of inputs, we can't really call it fuzzing, because fuzzing is supposed to run infinitely, not for a like finite amount of time. It is but just basically then testing, because the inputs are limited. But since libFuzzer is coverage coverage like does coverage based fuzzing, we are assured that the limited amount of fuzz inputs that we have in the QA assets will be a good indicator of the coverage of this test that we have. So I have like two distinct lines here. Since first targets are like run, and first targets are what like first targets is what we use when we want to run first base targets, and uh, using the first base targets, we run the first test with specific functions different from unit test and specifying rules. So I have like one distinction of fun, which is a first target, but in multiple files I don't specify one first target, and it will then run for a lot of targets Then we will merge the profiles and then create a report. This is very similar to this PR. So I guess doing this only will be sufficient. Tests have passed and we can generate profile data. Okay, so the profile data should be generated and build coverage.prof data. Yeah, so here it is. The prof data has been created, but we won't be able to understand it. It is kind of a gibberish based. So now we only have the LLVM curve generation step. Yeah, so this warning of 62 functions having a mismatch is because of the shared libraries and optimization problems that we have in our code base. So this is not really a problem of our code base, but the coverage interpreter itself. So this for now can't be avoided as this is a LLVM problem. And this is kind of a harmless problem. This won't affect how the coverage has been generated or what the coverage is generated for. We can now see our coverage report that we've generated. You can see that we have a function coverage, instantiation coverage, line coverage, region coverage, and a branch coverage. And we have a good amount of coverage, almost 100% for all. So yeah, so this is basically what we get. Now going into the questions and club. What are the different types of fuzzing and which one libFuzzer uses? So libFuzzer uses coverage-based fuzzing or coverage-guided fuzzing to increase the coverage. And what are the different types of fuzzing? You can name them as random fuzzing, mutation-based fuzzing, coverage-guided fuzzing, and uh, the other fuzzing that I mentioned. And how is the lcov generated report different from the libFuzzer generated report? So lcov is basically a wrapper around the gcov is a wrapper around lcov. Lcov essentially uses LLVM cov, but it has some slight modifications. So there isn't much of a difference between the reports generated, but they are different tools. Gcov is gcov is supposed to be compatible for multiple languages, and we don't have to do this manual LLVM cop show in them to generate a report. So basically, this is the difference. While the fuzzer we'll have to manually create a profile data and do this LLVM cop show step. And how does libFuzzer generate report for non-C++ code? So I have explained, we have an object created and we have a raw profile created. Raw profile is generated from the tests that we have. Test can be in any language. These raw profile are then generated, like converted according to the object files, and object files make them into an executable, then that can be run on libFuzzer. Sorry, not on libFuzzer, but on code coverage generator in our compiler, which will make it like C++, which like generally like which removes this distinction between C++ code and any other code, but now it's only a bytes, like it only makes it in bytes arrays and all, which then can be understood by any other machine. So this is how then it is generated. Like the libFuzzer helps us to generate coverage reports for non-C++ codes, and how can optimizations affect source-based coverage reports. So while creating this PR, there was a comment of using debug flag to create coverage reports. The reason behind that is this debug flag will then use, yeah, so this is the comment. So the debug flag will use this 00 flag. So what this 00 flag does is it removes any optimizations that you have, that the compiler makes. So while optimizations are being used, special jump instructions and special instructions are used to like fasten up the process of code generation. So when we are mapping the coverage data to the source, we can have some mismatches because of the optimizations. So this was the concern of this comment. And to remove optimizations, it was uh, like suggested to use 00 flag. But then later on, after a good discussion, uh, it was then uh, understood that since the doc only mentions 02 and there has been no mention of 02 like having bugs about this different like we won't be able to map the code to the coverage data. uh, we decided that we will only be using 02 flag only, and until and unless there is a bug reported, we won't be using 00 flag. So yeah, like this was the result of the discussion, and the answer to the question on how optimizations can affect source-based coverage reports. It can basically create differences when mapping the coverage data back to the original code. Yeah, like this is about the PR Club for today, and thank you everyone for joining.